Alright, cubics. Let's look at cubics in particular. The perfect cube. There's your pattern. A cubed plus 3a squared b plus 3ab squared plus b cubed. Powers of a are going down by 1, the powers of b are going up by 1. The two powers always add up to be 3. When it's negative, the signs alternate. Plus minus, plus minus. So in general, okay, we could generalise this. If you have a whole heap of them cubed, you will always get this pattern. A cubed plus b cubed plus c cubed. So all the terms cubed. Then you always get 3 lots of all the possibilities where one of the pronumerals is squared and the other one's to the power of 1. Notice again, the two powers add up to be 3. But you also then get 6 times all the possibilities when you grab 3 different ones. So in this case, A, B, C. So as another pronumeral, you'd also have an A, B, D, a B, C, D. What one have I left out? A, B, D, I think I've left out. So you'd also have that as well. That's the general pattern. Difference of two cubes always starts with A minus B. A minus B cubed, A minus B. That's why with difference of two squares, whilst it's not wrong to write it the other way, probably the most correct way of writing it is A minus B, A plus B. Always start the way the question looks. So A minus B. What happens in the other parentheses? Okay, you get A squared, AB and B squared. Be very, very careful. It's so easy to make that 2AB because you're so used to writing it with a quadratic. It's only AB. Powers of A start at 2, go down by 1. Powers of B go up. They add to give 2. Why only 2 in a cubic? Because the other one is in the first one. That gives you power 3. So we also have a sum of 2 cubes. We don't have the sum of 2 squares, but we do have a sum of 2 cubes. But it's very similar. Starts with what it looks like, A plus B. Still got the same pronumerals you'll notice in the other one, but now the signs alternate. It goes plus minus plus, plus minus plus. So that's the sum of 2 cubes. Know the pattern, saves you time. I got 2a minus 5 all cubed. Then, not saying you'd write this down, it might be in the head, but you know, first one cubed minus 3 times first one squared, then the second one plus 3 times the first one, second one squared, minus the last one cubed, we end up with our answer. Sum of 2 cubes, because 8 of course is 2 cubed. So it starts with, well, again, you wouldn't write that line down, but you think, oh, right, they're both cubes, so it starts with x plus 2. Then it's x squared, the product, so 2 times x, and then 2 squared, signs alternate for this one, so plus minus plus. Difference of 2 cubes, so that's what we're thinking. Starts off y minus 3a. First one squared, the product, 3ay. Last one squared, 9a squared. That's your pattern. In general, if you have a to the power of n minus b to the power of n could be anything, always just start off with what it looks like, so a minus b. And in the second one, it always goes a to the n minus 1, powers are going down by 1, then the other pronumeral, powers are going up by 1. The two numbers should always add to give the same thing. We don't have a formula, you see, for a to the power of n plus b to the n. I'll show you why when we do our examples. So if I have x to the power of 5 minus y to the power of 5, it starts with x minus 1. Powers of x going to start at 4, go down by 1. Those two powers always adding up to give 4. Here's the sum. The reason we don't have a sum is because I can rewrite this like that. Plus 1 is the same as minus 1 to the power of 7. And I use the formula for a to the power of n minus b to the power of n. So we end up with that. And all that happens is it's exactly the same idea. Start off with what you start off with. It's still got powers of going down by 1, powers going up by 1, but now they alternate, plus minus, plus minus, plus minus. But this is why we don't have a formula for the sum of 2 squares, for instance, because I can't do that trick when the power's an even number. Okay? I can only do that trick when the power's an odd number. Alright, there we go. That'll do us.